Hello, welcome to my channel The X. Ever found yourself intrigued by the way certain materials are attracted to magnets? Well, let's unravel the mystery together. We're talking about a fascinating concept called paramagnetism. Unlike diamagnetism, where materials are repelled by a magnetic field, paramagnetism showcases a different behavior. It magnetically pulls in. Paramagnetism is a form of magnetism, where certain materials are attracted to an externally applied magnetic field. Now, you might wonder, what materials are we talking about? They are known as paramagnetic materials. These include certain metals and their compounds, like aluminum and oxygen, which exhibit this unique magnetism. So, what happens when these materials meet a magnetic field? They align themselves according to the field, making it stronger. It's like they're charmed by the magnet's allure and they just can't resist it. Paramagnetism, in essence, is a fascinating phenomenon where materials are drawn to a magnetic field. But how does it work? Let's delve deeper. So, what makes a material paramagnetic? Well, it all comes down to the atomic structure of the material. You see, all atoms consist of a nucleus surrounded by a cloud of electrons. These electrons occupy regions of space known as orbitals. Now, in many materials, these orbitals are filled with pairs of electrons. However, in paramagnetic materials, some of these orbitals contain unpaired electrons. Why is this important, you might ask? Well, electrons are not just tiny particles with a negative charge. They also have a property known as spin. This spin gives each electron a tiny magnetic field or a magnetic moment. In most materials, the electron pairs are arranged so that the spins cancel each other out. But in paramagnetic materials, the unpaired electrons mean that there are magnetic moments that don't get cancelled out. When an external magnetic field is applied to a paramagnetic material, something fascinating happens. These unpaired electrons, with their individual magnetic moments, align with the external field. This alignment creates a net magnetization in the same direction as the applied field. What does this mean in practice? Simply put, it means that paramagnetic materials are attracted to magnetic fields. The strength of this attraction depends on the number of unpaired electrons and the strength of the external field. But here's an interesting fact. The alignment of the unpaired electrons, and hence the magnetization, is temporary. As soon as the external magnetic field is removed, the electrons return to their original random orientations and the material loses its magnetization. So, it's the unpaired electrons in these materials that make them paramagnetic. But what happens when the magnetic field is removed? What do you think happens to a paramagnetic material when the magnetic field is no longer present? Well, the answer may surprise you. Paramagnetic materials, you see, rely on external magnetic fields to align the magnetic moments of the unpaired electrons. Without this external field, these electrons are like dancers without a choreographer. They randomly orient themselves due to thermal agitation. This random orientation cancels out any net magnetic field, effectively eliminating the magnetic attraction that was present when an external magnetic field was applied. So, imagine you've got a small piece of aluminum, a paramagnetic material. When under a magnetic field, it's like a disciplined soldier standing at attention. But remove that commanding field and the aluminum snaps back to its usual non-magnetic self. So, without the magnetic field, a paramagnetic material loses its magnetism. But where do we see this phenomenon at play in our daily lives? Stay tuned to find out. Paramagnetism might seem like a complex phenomenon, but did you know it has practical applications in our daily lives? Let's dive into some examples. Firstly, the medical field greatly benefits from paramagnetism through magnetic resonance imaging, or MRI. MRI machines use powerful magnets and radio waves to create images of organs and structures inside the body. The paramagnetic properties of certain molecules in the body enhance the images, providing doctors with a clearer view. Another fascinating application is magnetic levitation, often seen in high-speed rail systems. The paramagnetic properties of certain materials allow them to be levitated above a magnetic field, reducing friction and enabling faster, smoother rides. Lastly, in the mining industry, paramagnetic minerals can be separated from non-paramagnetic ones using a magnetic separation process. This is crucial in extracting valuable minerals from ores. So there you have it. Paramagnetism is not just a fascinating phenomenon, but also a useful one. To sum up, paramagnetism is a captivating and practical element of physics. It's the phenomenon where certain materials are weakly attracted to a magnetic field thanks to their unpaired electrons. Delving deeper, we understand that this attraction rises and falls with the strength of the magnetic field. Remove the field and the attraction ceases. From MRI scanners to data storage, paramagnetism finds numerous applications. So, the next time you see a material being attracted to a magnet, you'll know it's the unpaired electrons doing their magic. Thanks for watching. Please subscribe my channel and don't forget to share. Have a nice day.